been interested in this field long before COVID. And so there's a whole set of tools that have been developed as part of a spin-off from the Washington team at the StatNet group. And it's due largely to Sam Jenness, who has done just absolutely remarkable work in this area, in terms of linking statistical models and networks to formal epidemiology. Sam may or may not know this, but he's responsible for delaying Martina's retirement by at least 10 years because she was completely fed up with the world she was in until she found this brilliant student to work with and said, you know what, there's still hope in the world, and kept going. So you know, that's a win right there. So Sam, thank you so much.
Thank you. And Martina finally retired last year, so I guess my work is done. I put all these slides up on online. You can get them at the address here. I'll flash that at the end. I have a bunch of links that are in the slides at the end for resources, so if you want to download the slides, you'll get all the links at the end too.
Sam, I'm going to interrupt you before you get started. We're going to do a room mic.
Okay.
For some reason,
We can't. I should have done this too. But yeah, apologies about that.
There we go. Okay. Can you hear me okay? Okay. So I just want to start by acknowledging all of my collaborators on this work, in particular Martina Morris and Steve Goudreau, who are really the instigators of the work that I've built in EpiModel, and of course all the scans on all the work of the larger StatNet group, including all of Carter's work and Pavel Krivitsky and everybody else. So today I'm going to go through some motivating examples for network-based epidemic modeling, and then have a bit of background and motivation for why we built EpiModel the way we built EpiModel, the types of things that it can do, and then end with some of the resources to point you in the right direction if you're interested in the future. Really, this hour is condensing a 5-day workshop in and of itself called Network Modeling for Epidemics into an hour, so there's not much I can do, but at least I can point you in the right directions if you're interested. So just hearing what some of the topics were discussed yesterday and looking at your syllabus for this week, I just wanted to highlight at the start what I think EpiModel does in terms of the social network analysis / network science boundaries and where we're kind of pushing what we're able to do. First, we're modeling dynamic contact networks. So these are temporally evolving networks with tergums, with temporal ergums. They are data-driven, so these are agent-based models of disease, but they're highly parameterized with primary and secondary data. And for our network data, this is sampled egocentric data. We heard a little bit about that yesterday. All of the research level models that we publish in papers are also multi-layer networks. And these are networks that are representing different types of contacts on the same set of nodes. So this might be, for example, different types of sexual partnerships among the same group, and each layer has a different set of formation and dissolution predictors in those models. One key thing here that we're doing that's complicated, but we've figured out over time, is that there's temporal feedback between the demography and epidemiology, like everything that's going on in the population that's not the network, onto the network. And so they're always talking back and forth between the network structure and everything else that's going on in the simulation. We've also developed, because these are, in one sense, big data models, a network representation framework that's rooted in the network package, but removes a lot of the stuff that we don't need for faster simulation, called Network Light, that just is able to represent the core network features of undirected binary networks with no missing data, and it speeds things up significantly. And on top of all of that, we're adding epidemics. Okay, so the first bit that we had to do was figure out all of these network features, and then the epidemic simulation on top of it is, in some parts, the easy part. So some motivating examples that are rooted in COVID. two papers that we did over the past couple of years. One was concerning the spillover impact of COVID and what COVID did to us sociologically and with respect to our healthcare on HIV and STIs. And these are the diseases that I work on primarily. People are still having sex, so why are STD rates dropping? The New York Times asked, is it because maybe the contact rates for sexual partnerships are declining, or there was a blip in those contact rates for long enough that it drove down STD rates, or was it because there was a disruption in access to STD screening services? So the cases were, the infections were happening, but the reported cases were not, or we weren't seeing all those cases. So we built a network-based model to explore the relative importance of those two things as they're sitting on top of each other, with a multi-layer network for sexual partnerships. So here's this multi-layer network framework where we have three different types of sexual partnerships: main, casual, and one-off partnerships. They have the same node set but different edge sets. They're primarily distinguished with respect to their dissolution, so how quickly they dissolve given that they exist right now. So one-off partnerships are instantaneous ergoms, whereas the main and casual partnerships have some durability to them. But there are differences also in the formation and dissolution models. So here's what some of the results look like, where we said, all right, we started the model out at 2019 levels, and then COVID started in March 2020. There was an immediate reduction in sexual contacts that occurred at that first dashed line on the left. And what happens to HIV, and what happens, that's on the left, and what happens to bacterial STIs, that's what's on the right, going specifically. The green line is looking at the scenario in which only sexual behavior is changing. The red line is looking at the scenario in which there's a disruption to services that has this kind of side effect of increasing risk overall, and the blue line is combining those together. Long story short, if you combine them together in that blue line, the actual longer-term impacts for HIV are minimal. They kind of stay at the stationary 2019 levels, but there are bigger impacts for bacterial STIs because we could have this period of sexual distancing that disrupts the overall transmission dynamics if we put the two things together. And then we did lots of exploratory scenarios where we looked at kind of the timing of how long the sexual distancing lasts versus the timing of the disruption to the clinical services lasts, and kind of mapped out all the potential scenarios. This was in like early 2021, so we still didn't really know how long everything was going to last for. Another motivating example is a model specifically for COVID itself in the cruise ship environment. So who takes a cruise during a global pandemic? Apparently a lot of people in Florida. And even after there were a large number of outbreaks in multiple cruise ships, people still took cruises. And there was like report after report of what was going on. One of the early outbreaks for COVID in February 2020 was in the Diamond Princess cruise ship that was docked out of Japan. And we built a network model to try to understand what the potential prevention strategies would be possible only with diagnosis and case isolation, given the highly structured and segmented network features that happen on a cruise ship, where people are passengers or crew, and if they're passengers, they're in particular cabins, usually with a spouse or a significant other. Most people travel in pairs, but they have like random sporadic contacts with other passengers and also the crew members as well. So this again was a multi-layer dynamic contact network in which the layers here represented the types of contacts that occurred from guest to guest, passenger to passenger, crew to guest, or crew to crew contacts as they evolved. We tried to put people in this kind of diagram of the network structure where they were assigned to particular cabins and sectors of the ship, and there was a lot of sectorization, particularly after the outbreak was detected and they shut down the entire ship, meaning that people were essentially like jailed in their cabins until the ship came back and docked and there was a quarantine. So we looked at different control-based strategies after the outbreak. We started with prevention-based strategies, like even before the outbreak takes off, of what was possible. So these are calibrated models. These really do speak to external data that we're fitting the model to. We take a look not just at the data related to the network features, but also the primary data related to case reports, and fit uncertain parameters like the transmission probability and other features of the model that parameters of the model we don't know a lot about, to replicate the case curves that are observed. One of the data points that we had for this model was the actual report of cases over time across the span of the month that the ship was operating. On day 15 of the outbreak, the ship went into this lockdown mode, and all of the cases, essentially dropped because all the passengers were contained. But we asked a lot of what-if questions of what if it had been earlier versus later? How much could we have caught if we started that lockdown at a different point? And how much would protective equipment like masking actually prevent in this scenario, given that most of the contacts were actually passenger to passenger within the cabin. So even after the lockdowns occurred, it was questionable whether masking, full-scale masking, was going to happen. So those are two examples, and I just wanted to kind of highlight what math modeling for epidemics is doing in general for the non-epidemiologists in the audience, and show how it kind of nicely interfaces with network science methods. Epidemic dynamics are inherently characterized by a lot of nonlinearities. We see this in emerging exponential growth for emerging infectious diseases, a case like Ebola outbreaks in West Africa, but also prevention strategies for the scale-up of things like vaccines, for cholera, where there is potential for indirect benefit from others in the community that are receiving this vaccine. This is called the herd immunity effect. This is largely driven by the fact that there's this ongoing feedback loop between the population and the individual. So if the overall rate of infection or the force of infection is driven by your rate of contacts plus the transmission probability per contact, those might stay the same, but what might change always over time is the prevalence of disease in the population. It might go up and down, and so the overall number of cases that are happening, the incident cases that are happening at any time point are constantly changing. Those same type of nonlinearities happen on networks too. This is a nice paper from Martina Morris demonstrating that even small changes in the mean degree, shifting people from one to multiple partners, has a dramatic impact on the overall connectivity of the network. And you can imagine from a pathogen perspective which network that a particular virus would rather be sitting on top of and flowing through. So Jim had this great introduction on agent-based models in general, and I just wanted to compare kind of what's going on in terms of generating networks in epidemiology, because there are a lot of instances in epidemic modeling where they're called network models or models on networks, but they're actually more agent-based models, and I want to draw a contrast between those two things. Many agent-based models, for epidemiology, the network is an emergent property from a series of dyadic choices, individual over dyadic choices. And there are different approaches to constructing that overall network, but a most common one is this so-called stub matching algorithm. I'll show you an example of that in a second. In contrast, a statistical network model, like an ergom or a tergom, has either a global or an individual dyadic representation, and we have a regression model approach to provide an inferential link between those levels. In a lot of agent-based models, the network generating algorithm kind of looks like this. This is an example from a large-scale, long-developed HIV model called EpiModel, developed by the Institute for Disease Modeling, that has heterosexual contacts between men and women. And they generate a network by having essentially like men line up in a queue, and there's a propensity for age mixing, so like selecting partners that are close in age to yourself, that's rooted in data. The men in the queue have a certain possibility of different female partners, and if the highest probability match is available, then they'll match with that partner, and then they move on to the next person in the queue. And if that match is not available, then they'll go to like the next available partner in the list, in the least preferred list. So this seems like it might work out pretty well for actually generating a network structure. But one of the challenges, if we look at the network from a top-down perspective, is that if we have one or two rules for the network generation, we might do pretty well. But if we start to have more and more rules for what generates what actually goes into the formation and dissolution of partnerships, things can break down pretty quickly. From a top-down perspective, it might look like any focal node, like the node that's highlighted in black here, has a kind of independent set of choices of what partners to select. But if we look at it from a global network perspective, any one of those choices has different implications for the other partners of partners in the network, and generating different distributions of degree and concurrency and other features that we might be interested in the model. It's often difficult within stub matching algorithms to abstract from the algorithm to ask counterfactual questions. So what happens if the degree changes and everything else might stay the same? So instead we use ergoms, and you've probably seen this formula 100 times already this week, but this is our general approach. The network data that we feature in network-based epidemic models varies, and we can use a combination of primary and secondary data. A lot of the work that I do in my group goes out and collects primary network data for incorporation specifically into these types of models. So we use an egocentric network framework. You heard about that yesterday, in which we go out into the world and ask people about their contacts, sample the egos and ask people about their contacts, both about the features of the contacts and the features of the partnerships or the contacts themselves, so edge level covariance and nodal level covariance. So one example of this in the HIV context is my ArtNet study. So this went out, and this is a web-based study that collected data on about 5,000 men and 16,000 of their partnerships, and we collected all that we needed to do all of our HIV and STI modeling. What we're building into these agent-based models now with the integration of this data and Turgums is also other GLMs, other generalized linear models, to do that same type of regression analysis and then prediction from the data where we have primary line level data. And I think this is kind of unique in terms of disease simulation models, is we can have a full-scale model that takes data in various components of the processes that we're interested in modeling and simulates from it or predicts from it in ways that address things like confounding and stratifications and interactions that are often a challenge for many agent-based models that only take marginal distributions across like all of their parameters. Here's another set of studies where we're doing this for respiratory diseases. So I work in TB, I work in COVID, and I've worked also in correctional health settings, so jails and prisons, for the transmission of different respiratory diseases. All of these studies are kind of using data diaries or contact diaries to collect the recent contacts that people have had over a certain period of time and aspects of those contacts that are relevant for disease transmission. So on the left-hand side is the data. On the right-hand side is some model for the process, and this can be very flexible related to the question of interest. I wanted to show you an example of what it looks like for our HIV transmission models among men who have sex with men. Again, these are multi-layer networks, so this is just one formula out of 3 that we're using where the propensity for forming edges is a function of edges, so like overall density, mixing on age and race, heterogeneity in mean degree in age and race, and then some non-parametric degree distribution terms, mixing on sexual role class. And I also wanted to highlight here what allows us to be a multi-layer network is that there's a term for heterogeneity in degree of one network as a function of degree in another network. So we're looking time step by time step to see what a person's casual degree is, and then feeding that into the main network model to determine the main degree. As you might imagine, if you have a high casual degree, you have a low main network degree, and vice versa. So they're kind of adaptive, and they can change over time. Fit the model, and hopefully it fits, and do lots of diagnostics on it, and simulate it forward. Now, the critical thing for infectious disease modeling for this framework to work, and spent years and decades to test this out on a lot of edge cases, is that these properties hold, these fit properties hold, even if the network size and the composition changes. And so that's the next thing I want to talk about, is just to show you how that kind of feedback occurs, and what we do about it, and how it's built into EpiModel. So more generally, we have to always think about time within epidemic modeling, and modeling over networks. And Jim talked about this a little bit, of whether we're modeling on networks or modeling of networks, or putting the two together. But one of the key questions we have to ask is whether the nodes are changing, whether the edges are changing over time, or both. And for different diseases, we make different choices based on the time scale of those diseases. For an acute immunizing infection like COVID, we may get away just fine with having a static network, because things move across that network so quickly, and the length of the edges, the duration of, say, your family or household or office-based contacts, is longer than COVID is. For something like HIV, the partnerships that you have for sexual partnerships might last months or years, but HIV is a lifelong disease of decades, and so we always have to take into account the fact that the rate of change in the network is faster than the rate of change in the overall, in terms of the overall disease. So we have to make that decision. And we also have to ask, if it is dynamic, how does the network adapt to all of the changes that occur within the population structure over time? So the first bit is easy for me as a non-statistician, because it's already been developed by Pavel and lots of other people in the StatNet team, but we're using Turgams to model how the network edges are changing over time as a function of a formation and a dissolution model that are linked but that are independent. But we might ask different types of questions of this evolving network and make different decisions about how to incorporate all of the other processes that we care about for the disease transmission process. On the simplest level, we might just ignore everything else besides the network and have some summary measure that quantifies how quickly a pathogen could move through a network, say if the transmission probability were 100%. If as soon as you got into contact with another person, there was a transmission event. And there's this nice measure called the forward reachable path that quantifies this for dynamic networks. It's built in within the temporal SNA package, TSNA, and we nicely summarize it here in the HIV context. But essentially, it's counting up the reachability over time as people are forming and breaking those edges. So you have this indirect connection with partners and partners. In one sense, this is somewhat analogous to an R0 measure in epidemic dynamics. So that might be your first step, but when we want to introduce epidemics into the network, we have to think about what the relationship and the feedback between the epidemic dynamics and the network structure will be. Many models of epidemics on network assume something like the middle here, where there's no feedback between the two. So what happens is there might be a dynamic network that's simulated over a time series from time 1 to time n, And then we go back to time 1 and simulate the disease dynamics on that already simulated network. And that assumes that everything else in the model besides the network simulation has no interacting effect on the network simulation itself. If that's not the case, and there is interaction or feedback, what we have to do is time step by time step do a resimulation of the network that takes into account all of the other updates in the population, and do this every single time step. And there's a constant look back and forth in between the two components of the model. So what might what might change over time? In the epi context, the node set might change, or the attributes of the nodes might change. The node set can change in epidemic models due to demographic churn, birth, deaths, and migration. And this can either be slow and incremental or shocks to the system. Sorry, I'm just going to get a little water. So the demographic churn might be slow and incremental, like a longer-term growth in the population size over time, or it might be a shock to the system, as might occur with a very deadly disease like Ebola, or some network shock like what happened on the cruise ship. In addition to that, attributes of the nodes might change. Key attributes that we care about are those that are actually referenced in the ergom formula. So if the attributes that are in the ergom formulas that guide things like age mixing or mixing on degree on diagnosed disease status are changing over time, those attributes are changing, and therefore the network simulations have to adapt to those changes over time. Also here relevant is that idea of the multi-layer networks, where the current degree in one network influences the degree in the other networks over time. Fortunately, for the latter issue of changing nodal attributes, there's been a lot of study to see that this performs in a predictable, usually predictable way that takes into account like what's happening in the network. But the first issue, when the node set is changing, gets a little bit more complicated, and we've developed some adjustments and workarounds to deal with this in EpiModel. So the first issue happens when the network size and composition changes. If we just apply the coefficients for a tergum as is without any adjustment, when we have a network of changing size, we're going to have density that's preserved in the network. That might not be what is intended, given sociological data that says when people move to different population sizes, they tend to preserve mean degree over density. But fortunately, preserving the mean degree requires just a minor adjustment to the edges coefficient within the model to update based on the population size. So this is equivalent to partitioning the original edges term into an offset, and then updating the offset as the population n changes over time. Another complication for what happens with vital dynamics is the fact that relations tend to break up when one of the partners in a relation dies. And this is largely inconsistent for how we collect data and we parameterize them within models. So when we're fitting our dynamic network using static data, such as the examples that I showed, they're usually reporting on contacts that they've had in the past 3 months or a year or whatever time frame, and those are usually living contacts. And there might be an overall propensity for partnership dissolution that's a function of the average duration of those contacts or partnerships. we had no information about death within those network data that we collected. And so if we simply put that into the model and don't make any adjustment, even if we correct the overall population size using the formula that I showed in the previous model, we'll see two features of the network reduce below the expected values that we want. And one of those is the average duration of the relationships, because as people are dying, they're reducing the length of the durations that are coming out of the simulations. And two, the average number of relations are also drawing that down. So both of those factors in our model diagnostics will be off. Some of that might be actually desired. We might actually want a network that's responsive to those demographic features. In one sense, that if we have a huge outbreak that kills off a large portion of the population, we might want to account for that in the fact of the models reducing the mean degree of the population and reducing the durability of relationships. But in many cases, that's not the case, and it's an artifact of our data collection and not what we want to actually build within the model. So we have another correction to be able to handle this, and we call this the so-called death correction. And we basically adjust for this competing risk of edge dissolution that's on top of the already calculated dissolution rate of edges that is in the model. And we add this basically an extra bump of how long relationships will last that take into account this competing risk. This gets a little complicated for dissolution models that are non-homogeneous, meaning that they're not edges-only dissolution models where there's some structure into the average duration of edges that might take into account attributes and mixing and things, but it generally follows this norm. So those are the kinds of things that we have to think about and work through when we're figuring out how to adapt a tergum into a context where there are exogenous changes to the population or network structure over time that are, in one sense, interfering with what the tergum does. And with all that figured out and built into software, then we can start putting some epidemics on top of it. And this is, in one sense, again, the easy part. The dynamic network structure in an epidemic modeling framework, I like to think about as like a big force of infection parameter. Instead of having one parameter, more like one lambda parameter in an SIR model, you have this massive parameter that's feeding in all of the features of how contacts are occurring and how they're changing over time. As long as we have that, and put it into an agent-based model for disease transmission in the right place, that is the transition between being a susceptible person and an infected person in the population, then all of the general theory and framework and rules that we have for building an epidemic model, whether it's in a compartmental framework or an agent-based model framework, then follow through. So we can embed something like a complicated tergum in a simple SIR model for something like measles, or we can get more complicated and use that tergum in a more complex model for something like HIV, where there's many other components of the disease, transmission, progression, behavioral, clinical processes that we also want to be able to represent. So the EpiModel software tries to bring all of these tools and methods together in a single software package that you can use for multiple purposes. Number one, for teaching and learning about how to build models on networks. And number two is then taking what's in the built-in package and extending it out for research level models to answer new questions. So in one sense, this package, EpiModel, sits on top of a very big family tree of StatNet and uses all of the coding and methodological framework that has been developed in all of these StatNet packages. So it plays nicely with StatNet and then builds on top of StatNet. And we can do things like making animated movies of networks using like the StatNet NDTV package, using all the tools that you might have already learned. So like I said, EpiModel is designed for both learning and research extensions. And the underlying goal with this development is to build a singular tool that can do both at the same time and using the same kind of language and syntax. So we have a series of built-in epidemic models where you can just run them out of the gate and not change anything about the disease structure itself. You can just say, I want an SIR model or an SIS model, and be able to simulate that. And then you can take that same framework and like build out structure to the disease system that might be relevant for your research questions. So for the built-in models, they look as simple as these compartmental frameworks for something like measles or another SIR disease. What's fixed within the built-in models are the disease states and the transitions between those states. And what's modifiable are the parameterization of everything related to the network and everything related to the actual like transition rates for the epidemic itself. The general workflow for EpiModel is listed here and follows this kind of idea that we're working with sampled egocentric network data, but that's not it's not required. We can work with an observed census of the network and input it as a network object into EpiModel. But usually we're working with some kind of sample data because of the population scale that we're concerned about simulating a disease across are not fully observable. So we have a data structure that we're setting up with attributes. We're parameterizing and fitting a tergum and diagnosing the model fit to make sure that it's a good model, then parameterizing an epidemic model, simulating an epidemic, and analyzing all of the simulation data from it. And there's a series of functions that do each one of these steps within EpiModel and help you along the way. In terms of extending EpiModel, we take what we had within the built-in models and then say add a new piece to it. So we have a built-in model for an SIR epidemic, but if we want an SEIR epidemic, the E is the exposed or latent state within a model that all COVID models have an SEIR representation. There's some period in which you're exposed to the infection but not yet able to transmit to other people. That's the E state. What do we do within the disease model? Well, we can code up a module for EpiModel that essentially represents that independent state and the transition, those new transitions that are encoded in the model related to infection and disease progression that weren't in the base model. How to do that? Well, it involves a bit of code, and so you have to get comfortable with that. But we have a lot of resources to do that. And I just wanted to show you one example of the fact that people have used EpiModel for these purposes all the time. This is my favorite example of a research extension for EpiModel to model vaccination of Hawaiian monk seals against influenza. So they had network data on seals. They had a specific representation of influenza that they had to code up and build, and they put the two together with an EpiModel for this nice paper. So I just wanted to show you at the end here some of the resources that we have available. The principal resource for all of our training materials is our website for the Network Modeling for Epidemics course. So this is a week-long summer course, formerly at the University of Washington. This year and last year we've been taking a break to kind of rethink and redevelop all of our materials, and we're going to be coming back next year in person in Atlanta. But still, all of the materials for the course are up and online and available for self-study, and so you can work through all the materials that are here at this link. I just wanted to show you briefly an example of what it looks like to kind of build, to work with a built-in model and the types of data and analyses that you can do even right out of the gate without building out any fancy extensions. So all of our course materials are designed around the sequence in which we're building up from simpler models to complex network models. And I'll just go to one example from the third day when we start modeling diseases across networks. This is an SIS type of epidemic. So SIS means like susceptible, infected, susceptible, so people can go back and forth between infections and non-infected states, something like a bacterial infection like gonorrhea. So we get started by setting up the network, parameterizing the model for the network, using some sufficient statistics for the key features of the network that we care about. Again, these are rooted in the idea that we have egocentric network data that we've summarized in the appropriate way. We're parameterizing both the formation and dissolution model, estimating the model. This is estimating the tergum, running diagnostics on it, and ideally having pictures of the diagnostics that look something like this, where we have the simulation sitting right on top of the target statistics. Once we get through running the diagnostics, and we can parameterize the epidemic model and the epidemic simulation. The built-in models come with a kind of core set of epidemic parameters that are unique to the disease class that you're modeling out of the box. And you can simulate the epidemic model and then start to work with the data here. So plot the epi curves in different ways. Look at the network object that's color-coded by the disease status. And have other time-specific data summaries that might be of interest. So looking at the dynamic edge list from the dynamic network might be of interest if you want to track through the specific contacts that occurred over time. You can export the data and work with it in different formats. And so the other tutorials within this material, I'll just take this kind of framework and build upon it and show you how to build things like counterfactuals for the networks. So in this example, we're building a counterfactual model for what happens when we change the degree distribution in a heterosexual transmission model, in which it's essentially a bipartite model where there's no contacts between people of the same group, but we model that in a slightly different way here with a node match term instead, sort of like no mixing between groups. Sorry, that's so small. And the types of outputs that we get are similar, and just to show you just at the end, plotting the networks, we also have some features that might be of interest to epidemiologists that include being able to export things like a phylogram, which is the kind of transmission tree from one edge to the next, one node to the next node that they're in fact in that sequence, and be able to work with that data and maybe compare it against some genetic sequence data if those are available. So all the course materials are organized here, and they end up the week with working on those model extensions for how to build the extensions, like adding different compartments to the epidemic model, adding different types of interventions into the model, with all of the tutorials organized around these R Markdown tutorials that you can work through and read through at your own pace, and run all the R code that's included in there. So a couple other resources that might be of interest that are linked on these slides. Our main software presence is on GitHub at this link here. It's a useful place to ask us questions, to interact with us as developers and epidemiologists, file bug reports, and can actually contribute to the code as some of our users had. we have a gallery of examples called the EpiModel gallery that it might be a little intimidating to take a built-in model and figure out how to extend it for a complicated research question. And so the gallery is intended to be a kind of pathway or a template for how to do that. So you might say, all right, I want to take a SIR model and add that extra E, like exposed state. Well, we have an example of how to do that. And we have a kind of description of what that involves, some model code, and what the actual coding up that actual module looks like that then gets plugged into EpiModel. Many of the models that we run on research level scales are big and long to run because we're building models on hundreds of thousands of nodes. And in part that's due to the fact that we're trying to represent like full-scale population sizes, and another part that's to figure out kind of stable estimates for disease properties in small subgroups. So you might have a large population of 100,000 people, but like a small subgroup of a couple thousand of those that you care about, delivering an intervention to. So you really need a very large network simulation to be able to adequately represent the small subgroup. So we have this add-on package called EpiModel HPC for high performance computing systems that allows you to work with EpiModel on a HPC that you might have access to through universities or elsewhere, and scaling up different jobs and scenarios accordingly. And lastly, there are 83 and counting scientific publications that have used EpiModel. Some of those are not network models, they're compartmental models, but that might be inspiration for thinking about how to use EpiModel based on what others have done, including that Hawaiian monk seal model. That's all I have today. I'm happy to answer questions.
Questions or comments?
I have maybe a too simple kind of young question, but we talked a lot about infectious disease spread here, but as we know, it's not just infectious diseases that can spread through networks, it can also happen for not traditional disease spread. Do you think EpiModel is appropriate for modeling those kinds of things too, or should it really be used for more strictly COVID, tuberculosis, STD spread kinds of things?
Yeah, it was originally, yeah, sure. So can EpiModel be used for modeling other diseases that are non-infectious, or maybe even social diffusion processes or things like that?
Yeah.
Right. And the short answer is yes, as long as you have network data for them, or some kind of rooted, or kind of theory in how to like parameterize a network model based on that, and maybe it's purely a theoretical model that's sufficient for doing that. We have a great example in that gallery that I just showed for a social diffusion model. Okay, and so this is kind of similar to the complex contagion model that Jim was showing, where it doesn't take just a person-to-person contact for transmission of susceptible to infected, but it's like the number of edges that you have in your immediate neighborhood for diffusion to happen. So our primary group is epidemiologists, and we don't work on these models, a lot, but there are a handful, 5 or 10 of the published models in that wiki page that have done something like this. So like network diffusion on computer networks, network diffusion on sociological networks too. So you can take a look at those.
Fabulous, thank you.
I feel like this might also be, well, that was a question. Can you use EpiModel in reverse? So if I wanted to look at how HIV-related disparities changed by race from like the beginning of the epidemic in the U.S., could I somehow use EpiModel to go that way instead of going like that?
Yeah, so the question is, can you use EpiModel kind of to understand historical patterns in disease dynamics or something that's happened in history? Yeah, so yes, you can, but one of the challenges is is whether it's rooted in data or whether like the data to uncertainty ratio is too low. Are you going to have enough network-related data from the 1980s, if that's where you want to start out, to be able to answer these network questions, or is it going to be more of a theoretical model where you're just asking what if things were the same back 30 years ago, or what if they differed, and what could have produced the model today? So in contrast to some compartmental, like differential equation models that really try to map out like the historical trajectory of infectious disease dynamics over decades, with the reason that they can do that is because they have simple parameterization. They have like one force of infection parameter that they just calibrate to like a case curve that happens over time. These models have many potential parameters. There's so many ways that you could parameterize the network components of a model. You have sufficient certainty to be able to do that. Yeah. But we do have a paper in it's there. The primary author is Steve Goudreau, and it's in Lancet HIV, that it's looking at the historical HIV disparities by race in the United States. That's trying to answer that question with network models. So that might be some inspiration to see what's possible. Yeah. Yeah, so the question is, how do we take into account antiretroviral therapy and HIV models, and kind of like some of the longer term effects that might have? And it depends on the model. We've been pretty consistent about how we've modeled this. It basically just gets added as a module like this to this complicated model where we're tracking things like viral load and CD4 count as they evolve over time. And antiretroviral therapy has the impact of increasing longevity, keeping people alive longer, and decreasing viral load, and thus decreasing the transmission rate for infected people. And we parameterize that based on some clinical trial data that shows how quickly people respond to ART and how often they fail treatment, like how often the treatment leads to morbidity and mortality. But that's one of the many pieces of the model that we have for HIV.
Are there tools for metapopulation models for say the network of communities if you want to understand spread across communities, but you don't necessarily have a complete network for within the communities?
Yeah, so the question is, are there tools for metapopulation models, so like multiple networks spread across different communities? I just worked on a paper with someone who was doing this in a tribal environment in Bolivia, where these isolated villages, and each one of the villages had little sub-networks that were unconnected, kind of like a block diagonal constraint. So they weren't connected to each other, and they were connected in the broader network. So we were able to do that because each one of those sub-networks were relatively small. These little small villages. It gets really challenging, I think, to think about this on a bigger connected population level, where you might have a model for influenza across the United States in each city, and they're all connected, mainly due to computational constraints. There's kind of like a cap on the computational cost of fitting ergoms with millions of nodes, but otherwise it's conceptually possible.
Does that paper coming out?
Yeah, I can send you the link to that. Yeah. Okay. Well, thank you so much.
Thank you.